So these are taken from your homework this week. I was looking through the homework, and I guess I was specifically looking for a question that involved multiple objects, because those are really the situations where you do need to use a standard strategy. And that's why I think Andy was calling it multi-block strategy, because it's when you have multiple blocks with forces connecting them in some way, that if you're trying to work it out intuitively, then you will run into some problems. So this is the very last question on the homework set that you do 1 week from now. So I'm guessing most of you won't have seen this yet. I'm hoping the recorded video will be useful by the time you get to this homework. So let me illustrate the application of the standard strategy with this problem. So as a reminder to myself, this is what standard strategy says. And my apologies for slowness of my writing. In the edited videos, I usually cut this part out. So step number 1 is to draw free body diagram. And this is a 2-word phrase that packs a lot of meaning. There's a lot of thought process that should be going through your head as you're drawing free body diagram. 2, I like to say define coordinate axis. So define axis. And there's really one guideline in defining your coordinate axis is you look at the direction of acceleration. And the third step is really where it's getting obvious that I'm preparing for step number 4. Step number 3 is to break forces into components. And the sole reason to break forces into components is so that you will be ready to apply Newton's second law and write down the Newton's second law equations. So when you have a 2-dimensional problem, it'll be like writing the net force along the x direction is mass times acceleration along the x direction, and net force along the y direction is equal to mass times acceleration along the y direction. So let me illustrate these 4 steps with this question. And I hope you can kind of see what I mean, that if you're trying to solve this question without using the standard strategy, that you're probably gonna be stuck. So it says something about coefficient of kinetic friction between the surface and the larger block, and the coefficient of kinetic friction between the surface and the smaller block. It gives you the applied force, 10 newtons, and it gives you the value of the capital N, which gives you mass of both blocks. One is twice that, the other one is just that value. And if it was even asking for the acceleration of these blocks, then I think some of you might be able to do this intuitively. You'd figure out what is the amount of friction pushing this back, what is the amount of friction pushing this back. You get the net force, apply the force minus the friction, divided by the total mass. That should give you the acceleration. But unfortunately, what the question is asking isn't that, but it is the tension. And figuring out this tension is something that if you're trying to do it intuitively, that you'll eventually recognize that you are stuck. Because intuitively guessing, you could guess something like 10 newtons. And the system will say it's wrong because it's wrong. Or then you might try some other things. Like you might even do something like, all right, I know this is 10 newtons. So, take 10 newtons divided by the masses that get you accelerated. Okay, let me not list all the ways you can do this wrong, and instead show you the one way where you can do it right. So we start out by drawing free body diagrams. And what you should remember here is that you draw free body diagrams for the two objects separately. So let me draw one for the big block here, 2m, and a second diagram for the small block m. And drawing them separately reinforces that you only draw the force that is on that exact object. So for example, this applied force F here, it's acting on the smaller block M. So in the process of drawing the free body diagram, I won't be drawing this force F directly on the mass 2M. So, all right. So it feels like it's a little bit easier to do this with a small block M because it has it relates more directly to the applied force, which I'm given directly. So let me start out from here. So on this block M, I am going to draw the applied force F. That is the one thing the problem tells me, one force the problem tells me is acting on this system. So, all right, there's my force. And what I do is I keep asking myself this question. Did I draw all the forces in the system? The question said something about coefficient of kinetic friction between the surface and the smaller block at the value of 0.29. So it would be a very odd thing for the problem to say that if there wasn't friction force acting on the mass. So, all right, so I draw a friction force. The question gives me the coefficient. It doesn't give me the value of the friction force. So I'll draw it for now. And I ask myself the question, have I drawn all the forces? Then I hope, as you are looking at the friction force, and maybe something you read about the friction force, how the kinetic friction force is given by coefficient of friction times the normal force. That something is missing in this diagram. Where is the normal force? So the normal force is the force from the surface pushing the block up. So that would be an upward force acting on the block. And if that's all you had, then this should be accelerating upward as well. But there's always gravity. So gravity is pulling the block down. And actually, that's why the normal force is there. And if we want to cut some corners, we can guess from this diagram that the normal force must be mg. But actually, let me not do that because I think that has a potential to reinforce some bad habit that I've said. All right, so you have this diagram. And once again, you keep asking yourself this question. Have I drawn all the forces? And it's very easy to forget a force. So slow down, take a moment. Keep looking back and forth between this diagram here and this diagram here and see what you might be missing. Hope you found it. It's the tension force. This taut string here, it's applying a backward force on the block. So I should have also a tension force. All right, I think now I'm done. Once again, you should keep asking, have I drawn all the forces? And as you compare the forces you have drawn on this diagram to the physical picture here, hopefully you eventually convince yourself, yes, I've drawn all the forces, I'm done with this one diagram. So let me continue on with the mass 2m. So I guess now that I realize there's tension here, there's also tension here. And this tension should have the same value as the tension backward on the smaller block. There are many ways to justify it. You can give it as property of tension. One thing I like to think through is the fact that these are, in some sense, action-reaction force pairs. So they are equal in magnitude, opposite in direction. There are other forces acting on this big block as well. Let me just draw them without talking through too much about it. So there's a friction force pulling the big block back, F2N. And so to get the friction, you're going to need the normal force and the gravity, mg. So that's the free body diagram. And let's keep stepping through the standard strategy. It says define the axis. So here it looks pretty simple. It looks like everything's either horizontal or vertical. So I'll say that's going to be my axis. Horizontal to the right is my plus x. Vertical upward is my plus y. This question is quite a bit simpler because there's nothing to break into components. They are all already either along the x direction or the y direction. There's no diagonal direction. But if you find them, as you've seen in some questions earlier, you should be prepared to draw the triangle and break forces into components. So having done all that, now I am finally ready to do step number 4 and write down Newton's second law equations. And I want to start out by recognizing how many equations I have to write because I don't want to forget a single one of them. There are 4 equations I'm going to need to write. It comes down to the fact that I have 2 objects, and for each object, I need the x and y direction. So let me first write it all down. So net force for 2n in the x direction, that's 1. Net force for 2n in the y direction, that's another. Net force for smaller block m in the x direction, and net force for smaller block m in the y direction. All right, now I'm ready to copy all the information down into an equation form. So the very first one, net force for 2n in the x direction. So I look at, so this is what I mean once you have done free body diagram correctly and gone through steps 2 and 3. All you have to do in step number 4 is read off the information that is in your diagram. So as I look at diagram for mass 2m, I see 2 forces along the x direction, and the other 2 forces are all along the y direction. So the net force on 2m along the x direction will look like the plus tension, that's the rightward force, which I've already defined as positive, minus the friction force 2m to the left. And I can go, well, I can go one step further and write this down, but let me, I guess, leave that there. I'll come back to it later. So this should be equal to mass, which is 2m times acceleration. And y direction, you see that I have these 2 forces in the y direction. So you write those down. So the net force on 2n in the y direction is the normal force. Let me use the subscript to 2m so that I don't forget which normal force it is. Minus mg, oh, that should have been 2mg. 2mg, the weight, is equal to, and by the way we defined the axis, this should work out to be 0 because the block is accelerating up or down. All right, I'm done with object 2m, and I have to continue on. Following the standard strategy, it can be quite a bit long and possibly even tedious, but it's like a long walk. What matters is that step by step, you know what to do, and eventually you'll get to a destination where you will hopefully enjoy what you see. So let me finish writing down the equations for the smaller block m. It's going to be a little bit more complicated because there are 2 forces here. So, okay, apply the force F minus the friction force, let me call this F sub m, minus one more thing, the tension force. That's equal to the mass times the acceleration. All right, almost done, almost done here. In the y direction, I have the normal force minus the weight, this time it is mg, is equal to 0. All right. So even getting to this point, it was quite a bit long, partly because I was talking the whole time. So, so this is actually the end of standard strategy, kinda. Um, what I like to do before I say I'm ready is count the number of equations. Because if we don't have enough information, now is the time to address it. If we have enough information, great. We have a system of equations, and what we now should do is to solve it. And it's all just math, or maybe not just math, but so let's work through that. So we're first counting the number of equations. So number of equations, I have 1, 2, 3, 4. And now what I should do is count the number of unknowns. We don't know tension. That's kind of why we're doing this whole thing. If we knew what the tension was, we would put it in. Friction on the big mass. I don't think I know that. I'm not given that. I'm given the formula. Maybe that'll help. But for now, let me label friction force as unknown. And acceleration is also not known. The question isn't asking for it, but I don't know acceleration. Normal force on 2m. Now, many of you might get the temptation to kind of jump to this thing that you've seen so many times. N is equal to mg. And I want to just slow you down a bit, because later on you are going to see questions where that relationship isn't quite right. So for now, let me just label it as, I don't know what normal force is on the big block 2m, because I'm not given the formula. It's different from the weight where I'm given the formula. All right, let's keep going. Apply the force, I'm given that, I know that. And friction force on the small block, that I don't know, so I like that. Acceleration and tension, I don't know them, but I already marked them. And I have normal force in the y direction for the small block, and I don't know that either, so I just labeled it. So when you first look at it, it doesn't quite look okay, because you have 6 unknowns, and you only have 4 equations. So it feels like you don't have enough information. But hopefully, as you're staring at this and thinking about it, I hope you realize that you haven't used this information about friction forces that you know. That the kinetic friction force is given by coefficient times the normal force. So normal force is already one of my unknowns. So by writing it in other equations, I'm not going to be losing anything. But what I can do now is write these friction expressions instead of as its own thing. I can say, oh, following that formula, that's equal to the coefficient times the normal force associated with that friction force. So instead of it being general friction force, it's the kinetic friction force, which is the coefficient times the normal force that is associated with that friction force. And once you have that, then okay, I have 4 equations and 4 unknowns, and this is how you solve them. I can actually simplify this simplification quite a bit to say this is equal to, or this gives me the n to n, the normal force, is equal to 2 mg. Oh, so I guess I can just plug that in here. So let me do that, not waste too much screen space. So I have 2 mg is equal to that. And one caution I want you to take is always remember this step. First, to write down your Newton's second law equation in the vertical direction, and apply it to find the normal force, because there will be a few questions where you might be surprised by the fact that normal force is not equal to the weight. It's a portion of the weight, or sometimes it can be even greater. So you do the same thing here. The normal force on the smaller block is equal to mg. So plugging that in into the equation above, I have normal force is equal to mg. So one thing I like to kind of do mentally is, once I've used an equation in a system of equations to obtain some information I know, then I try hard not to reuse it. Because if I reuse that equation, there's a good chance I will create what's called a dependent set of equations. And I hope you remember that from algebra. You want independent system of equations. So as far as the independent system of equations go, now I have two equations and two unknowns, so it's solvable. And what I would do is, I am looking for tension, so I want tension as my final answer. So then what I do is I solve for the other unknown first. What that'll give me is a tool. A, acceleration as an expression in terms of something else, so that I can plug that expression into the other equation and solve for my final, the unknown that I'm really interested in. So let me solve this for A. Solving this for A, you get, I guess just divide the whole thing by m. So F minus mu mg minus tension divided by big mass M. So I plug that into equation 1, and doing that gets me this expression. Tension minus mu 2mg is equal to 2m times F minus mu mg minus tension divided by m. So you see that this m cancels out that m. I'm just simplifying as I go. And looks like I need to solve for tension here. T, and I have 2 or minus 2t. So imagine collecting them all on the left-hand side. So I have 3t, or I'm adding plus 2t to both sides. And I guess I need to write down the remaining two terms on the right-hand side. 2f minus 2 mu mg. And I have this term here that I need to move over to the right-hand side. So it becomes plus 2 mu mg. Oh, I guess this question kind of works out nice for us. These two cancel out. They didn't, I don't think they had to. I'm pretty sure they didn't have to. But they cancel out in our case. So, so we can solve for tension here. The tension works out to be 2/3 F. Oh wait, sorry, I made a small mistake. I'm pretty sure they don't cancel out. So the small mistake I made is they would cancel out if the friction coefficient were the same, but they are not the same, so they won't cancel out. Let me just label the friction coefficients carefully. This is the small m friction coefficient, and this is the big M friction coefficient. So I have minus, okay, mu m, and I have a plus 2 mu 2m. This is why it's important to label your symbols carefully and correctly. Don't reuse the same symbol twice. So okay, they don't cancel out. You'll just have to keep them all. You'll just have to plug in the numbers that are given in the question. But solving for tension nonetheless, you get, so you divide both sides by 3. Tension is equal to 2/3 F minus 2 times the friction coefficient for the small block times mg. and plus 2 times the friction coefficient for the big block times mg. And so this is an expression with everything known, with all the numbers given. We are given what the value of force is. We are given what the friction coefficients are. Make sure you don't mix them up. And we are given what the value of the capital M is. So you can plug those in, get a value for tension, and plug that in there. So even when you are following standard strategy, so maybe you can do this a little bit quicker if you're not talking the whole time and trying to explain what you're doing, but it is a still lengthy process. What it is solving for a system of 4 equations. And even though these are relatively simple set of 4 equations, it still takes a bit of time. So, this is not a trivial problem, but what the standard strategy allows you to do is it allows you to, trying to check if there's any participant. It allows you to break down a problem that might be too big to handle intuitively, to handle without a really systematic way of tackling it. And it allows you to tackle it systematically.